Lecture 3. Set functions. Let A be a non-empty class of set. A function mu from A into R star is called a set function if for each set E element of A there is a unique number mu of E element of R star. Mu of E is called the image of E under mu, where R star here is defined to be an extended real number. That is, R star is equal to real number union the set of minus infinity and infinity. Please note, if mu from A to R star is a set function, then the image of phi, that's the image of empty set under mu, is 0, which is element of R star. Finitely additive set functions. A set function mu from A to R star is said to be finitely additive if for disjoint sequence of set E1, E2 to En in A, the image of the union of Ek as k goes from 1 to n under mu is equal to the sum of the images of Ek as k goes from 1 to n. Example number 1. Let omega be a set of infinitely many points and A the class of all subset of A of omega. Let us define mu by mu of E equal to number of elements in E if E is finite, and is equal to plus infinity if E is infinite. Then mu is finitely additive set function. Example 2. Consider the following figure. This is a pentagon, a regular pentagon. Let this pentagon be the set E. Let A be the set of all triangles. And let us define the set function mu from A into R star as follows. Image of E under mu equal to area of E for all E in A. That's mu of A is the area of a triangle in A. Then mu is finitely additive. To show this, let us partition the set E as follows. And let this first triangle be E1. Let the middle triangle be E2. And let the third triangle be E3. Clearly, E1, E2, and E3 are disjoint subset of E. And E is equal to the union of the three. That is, E is equal to E1 union E2 union E3. Therefore, mu of E is equal to mu of E1 plus mu of E2 plus mu of E3. That's the area of this pentagon E is equal to area of this triangle plus area of this triangle plus the area of this triangle. So that is why the set function defined as the area of triangle in A is a finitely additive set function. Example 3. Let omega be half open interval from 0 to 1, open at 0, close at 1, and A the class of all half open intervals AB, where A is less than or equals to B and B is less than or equals to 1, A is greater than or equals to 0. If mu is defined as follows: mu of AB equals to B minus A if A is not equal to 0, plus infinity if A is equal to 0. then mu is a finitely additive set function. Proof. Let us define the subinterval ek as half open interval 1 all over k plus 1 to 1 all over k. It is open here and close here for k equals to 1, 2 to n. Then the image of ek under mu by definition is equal to 1 over k minus 1 all over k plus 1. Since 1 over k plus 1 is not equal to 0, recall how we define mu. Mu of AB was defined as b minus a if a is not equal to 0, and it is defined as plus infinity if a is equal to 0. But here, this is representing a is not equal to 0, so mu of ek is equal to 1 over k minus 1 all over k plus 1. Let us find the sum of these images as k goes from 1 to n. The sum of mu of ek as k goes from 1 to n will equal to the sum of this as k goes from 1 to n. Let us write this out in full, starting from k equals to 1 to k equals to n. When k is equal to 1, that will give us 1 all over 1, which is 1, minus 1 all over 2. So this will be equal to 1 minus half plus, when k equals to 2, that will be 1 over 2 minus 1 over 3 plus, when k equals to 3, that will be 1 over 3 minus 1 over 4 plus. If we continue, we will get to when k is equal to n minus 1, which will be equal to 1 all over n minus 1 minus 1 all over n. Plus finally, when we get to n, when k is equal to n, that will be 1 all over n minus 1 all over n plus 1. Now, observe that minus 1 over 2 plus 1 over 2 will cancel out. Minus 1 over 3 plus 1 over 3 will cancel out. Minus 1 over 4 plus 1 over 4 will cancel out. We'll continue that way until we get to minus 1 over n minus 1, which is around here, plus this will cancel out, and minus 1 over n plus 1 over n will also cancel out. So what we are left with is this one minus 1 all over n plus 1. So this sum is therefore equal to 1 minus 1 all over n plus 1. Now let us find the union of ek as k goes from 1 to n. This is equal to the union as k goes from 1 to n of the half open interval 1 all over k plus 1 to 1 all over k. This union will give us, of course, when k equals to 1, what you have will be 1 all over 2 to 1. When k equals to 2, that will be 1 all over 3 to half. When k equals to 3, that will be 1 all over 4 to 1 over 3. If we continue to when k equals to n, that will give us 1 all over n plus 1 to 1 all over n. Then clearly the union of all this interval will be the interval from 1 all over n plus 1 to 1. And therefore the image of this union under the set function mu is equal to the image of this half open interval under mu. And by definition, the mu of 1 all over n plus 1 to 1 is equal to this one minus this. It is equal to 1 minus 1 all over n plus 1. So what we have shown here is that the image of the union of ek as k goes from 1 to n is equal to the sum of the images of ek as k goes from 1 to n, which therefore implies that the set function mu is finitely additive. Let me show you what I have done by means of diagram. Here is our half open interval from 0 to 1. This is the interval from 0 to 1. It is open at 0 and it is closed at 1. So our ek is defined as the interval, half open interval 1 all over k plus 1 to 1 all over k. So when k equals to 1, you have half here, and the interval from half to 1 is this interval, which is E1. So E1 is obtained by putting k equals to 1. That is the interval from half to 1. When k equals to 2, we are finding E2. So this place will be 1 all over 3. And the interval E2 is this interval from 1 over 3 to half. It is open here and closed here. Then when k equals to 3, you have 1 over 4 here. The interval from 1 over 4 to 1 over 3 is E3. It is open at 1 over 4 and closed at 1 over 3. So we can continue that way. The interval is shifting to the left. Clearly you can see that E1 union E2 is the interval from 1 over 3 to 1. E1 union E2 union E3 is the interval from 1 over 4 to 1. So when you continue until you get to En, the union of Ek as k goes from 1 to n will be the interval from 1 all over n plus 1 to 1. Sigma additive set functions. A set function mu from A into R star is said to be sigma additive if for disjoint sequence of set E1, E2, E3 and so on in A, the image of the union of Ek as k goes from 1 to infinity under the set function mu is equal to the sum of the images of Ek under mu as k goes from 1 to infinity. We note that 1. If a set function is sigma additive, then it is also finitely additive. 2. Finitely additive set function may not be sigma additive. Example 4. Let omega be this half open interval from 0 to 1 and A the class of all half open intervals AB, where as defined before A is less than or equal to B, B is less than or equal to 1 and A is greater than or equal to 0. If mu is defined as follows: mu of AB equals to B minus A if A is not equal to 0, and it is plus infinity if A is equal to 0, then mu is not a sigma additive set function. Please recall that in our previous example, we showed that the set function defined as this on omega on half open interval from 0 to 1 was finitely additive. And also remark that a set function may be finitely additive but not sigma additive. So let us show that this set function, which was finitely additive, that it is not sigma additive set function. Proof. Let Ek as before be defined as the half open interval 1 all over k plus 1 to 1 all over k for k equals to 1, 2, 3 to infinity. This time around we don't stop at n, but the sequence goes to infinity. Then the image of this Ek under mu is equal to 1 all over k minus 1 all over k plus 1. Since 1 all over k plus 1 is not equal to 0. So let us now find the sum of this mu k as k goes from 1 to infinity, which is the sum of this as k goes from 1 to infinity. Let us write this out in full, starting from k equals to 1 to infinity. This is equal to, when k is 1, that will be 1 all over 1 minus 1 all over 2. That's 1 minus half. Plus when k is 2, that will be 1 all over 2 minus 1 over 3. Plus when k is 3, you have 1 all over 3 minus 1 over 4. Plus 1 k is 4 will be 1 over 4 minus 1 over 5. We'll continue like that till we get to infinity. Now, observe that minus half plus half will cancel. minus 1 over 3 plus 1 over 3 will cancel, minus 1 over 4 plus 1 over 4 will cancel. That means every term from minus half to infinity will cancel out, giving us this sum equal to 1. So we have shown that the sum of mu k as k goes from 1 to infinity is equal to 1. Next, let us find the union of ek as k goes from 1 to infinity. We recall we had earlier found this union to be equal to the union of 1 all over k plus 1 to 1 over k as k goes from 1 to infinity is equal to 0, 1 interval, have open interval 0, 1. So therefore, the image of this union under our set function mu is equal to the image of 0, 1 under the set function mu. But recall the definition that if what you have here is 0, then we define mu of 0, 1 to be plus infinity. So you can see here that the image of the union under mu is plus infinity, while the sum of the images of ek under mu was equal to 1. So we have seen that these two are not equal. That is, the image of the union of ek as k goes from 1 to infinity under mu is not equal to the sum of the images of ek as k goes from 1 to infinity. Hence, the set function mu is not a sigma additive set function. Example number 5. Let omega be half open interval from 0 to 1 and A the class of all half open intervals AB, where A is less than or equals to B, B is less than or equals to 1, and A is greater than or equal to 0. If mu is defined as mu of AB equals to B minus A, observe that we have redefined mu this time around, but it is the same problem. The second condition, that's the condition of saying that mu AB equals to B minus A if A is not equal to 0, equals to plus infinity if A is equal to 0. Those conditions are removed. So we simply define mu as this. If we define mu as this, then mu is both finitely additive and sigma additive set function. Sub-additive set functions. A set function mu from A into R star is said to be finitely sub-additive if for any sequence of set E1, E2, E3 to En in A, the image of the union of ek as k goes from 1 to n is less than or equal to the sum of the images of ek as k goes from 1 to n. And it is said to be sigma sub-additive if the image of union of ek as k goes from 1 to infinity is less than or equal to the sum of the images of ek as k goes from 1 to infinity. Example number 6. Let omega be a set of infinitely many points and A the class of all subset of omega. Define mu by mu of E equals to number of elements in E if E is finite, plus infinity if E is infinite. Let E1, E2 to En be arbitrary set. Then, image of the union of ek as k goes from 1 to n is equal to the number of elements in the union of ek as k goes from 1 to n. We recall that for arbitrary sequence of set that we can construct a sequence of disjoint subset fk of ek such that the two union will be equal. So therefore we can write the number of elements in union of ek as k goes from 1 to n as the number of elements in union of fk as k goes from 1 to n. And since fk are disjoint, the number of elements here is equal to the sum of the number of elements in fk as k goes from 1 to n, where fk is a subset of ek. This implies that the number of elements in Fk is less than or equal to the number of elements in Ek. That is, if we sum both sides of this inequality, this will give us the sum of, please, this is the number of elements in Fk is less than or equal to the sum of the number of elements in Ek.